All right, let's get started. One thing I noticed was that I was looking at the videos last time, and the first one was okay because the contrast was right for the screen. But the second ones, where I was writing on the board, it was pretty hard to read it because it was pretty zoomed out, and the contrast wasn't great either. So I'm trying different settings. I hope this will work better. I don't think anyone's done that because there was actually an error uploaded in the second video, and then the third lecture there hasn't been many views. So I assume no one's really. Has anyone tried that out at all? Even looked? No? Okay. I imagine you will when the homework starts being due is the thing. So you'll go back to them. Just know that the first 3 lectures, I guess, then aren't ideally recorded. Hopefully you can make out what I write on the board knowing what I'm already writing. But if not, then don't worry. Everything is in the slides. So you can get it off from the slides. It's just that the videos can be very handy because what I write out on the board can be a helpful kind of addition. From now on, I'm going to try to zoom in a little bit more. It's not an ideal setup for video because we kind of have the screen way up there and the thing on the side here, but you know it's better than a lot of places. So we'll make the best. We'll make do with what we have, but do come to classes too because you can't quite trust the videos to be perfect. Hopefully they'll be good enough though. So today we're going to keep going with a linear algebra review. We're going to then review some matrix calculus. And this one, I imagine, for a lot of people is going to be more new. You haven't seen this before. And so in that case, we're actually going to, I'll describe kind of all of it today. But then I'll also, whenever we use it in class, I'll kind of give a brief refresher about what I mean by different properties, the Jacobian, the gradient, and the Hessian in particular. I'll describe again what I mean by these things because it's not something you might all be familiar with. And then finally, we'll conclude and hopefully be able to finish up the start and finish the MATLAB review. That'll be a little bit different because I don't have slides for that. I'm going to use my computer and go through a bunch of examples, which I've actually also put on the website. But it's not going to be a set of slides. I figure putting the same exact code on slides is actually a lot less useful than just seeing me do it. So if you have MATLAB on your computer here, you're welcome to follow along. But you can also just watch the screen. It should be fine as well. So first of all, were there any questions from last time? We ended up, I believe, talking about this all ones vector, and we're kind of just blazing through different elements here of matrix, of linear algebra. Not by any means all of linear algebra, but just the parts that we're going to use a lot in this class. So first of all, were there any questions from last time? As always, feel free to interrupt during the lecture and ask questions, but see if there are any ones from last time. OK, so let's go through, just try to finish up linear algebra and then move on to matrix calculus. Talked about the all ones vector last time as being a special case of a certain vector where we can use sort of abbreviated notation, just the number 1 to denote not just the number 1, but actually a vector of whatever size you need that has all ones. And that can be used for things like sums and stuff like that. So this whole little section here is on special types of matrices, and the ones vector and the zeros vector and the identity are all special matrices. Another type of a special matrix is a symmetric matrix. Symmetric matrices, A in R, n by n, they have to be square because otherwise the matrix cannot be symmetric if it was not square. But these are situations where A is equal to its transpose. In other words, Aij equals Aji for all I and j. And this might seem like a very sort of special case, but it actually comes up a lot in practice. Right? So one thing we actually saw in linear regression already was this matrix phi. I guess I'll just write it like that, because let's see, phi was a matrix in R m by n, right? It had m rows, n columns, because it had one feature vector per row for m different elements and different input vectors. And in our derivation, we got this term phi transpose phi. Remember, our optimal theta here was this thing inverse times theta transpose y. That was our solution, our normal equations that solve these squares. But if we just look at this guy here, phi transpose phi, this is a symmetric matrix. And it's pretty easy to see that, right? Because if we take the transpose of this, well, the rule for transposing is that when you multiply matrices and transpose that, you flip the order and you transpose each one. So this is equal to this guy transposed, phi transpose, times this guy transposed, which is phi transpose transpose. And hopefully it's obvious that phi transpose transpose is just phi. So that's equal to phi transpose phi. That's true for, of course, I'm writing there just for any A in M by N. A transpose A is a symmetric matrix. We'll also see this come up a lot of times in power systems. When we talk about the matrices involved in power systems, what we'll find is that because the resistance of a line, for example, or just in general the characteristics of a line, transmission line, it doesn't matter if you talk about the characteristics from node I to node J or node J to node I, those are the same. You have same resistance between node I and node J and node J and node I, right? In a network, for example. And so a lot of matrices that we're going to encounter very naturally in power systems end up being symmetric matrices. So we'll see these a lot. And they have some very nice properties too, which I'm not going to quite get into yet. We'll sort of see them a little bit in practice. But symmetric matrices are actually very, very common in practice, even though it might seem like a very specific special case. All right, a few more special elements here. A diagonal matrix is a matrix, not surprisingly, that has zeros everywhere but it's diagonal. So for a vector d in R to the n, so this is a vector, an n-dimensional vector, we'll use this notation. We'll write diag of d. That is going to be a matrix which is n by n, where all the elements of that matrix are 0 except the diagonal ones, which are just the elements of D. So D1, D2, Dn here, and everything else is 0. Now these are actually extremely useful in practice. For example, the identity is just given by diag of 1. That would be in our notation, right? Ones is the all ones vectors. The identity would be diag of 1. That's not that useful. It's just for definitional stuff. But diagonal matrices are very useful for doing things like scaling the rows and columns of a matrix. So let's suppose that we have a matrix A, Rm by n, and I'll start by writing A in terms of its rows. So A1 transpose is the first row up to AM, AM transpose. Now let's think of what is, and we also have a vector D. Now what would the matrix be, this matrix? Sorry, D is an Rm here. D is an Rm. So we have a diag D, so that forms an M by M matrix. A is M by N. This, remember, is now going to be M by M. A here is M by N, so we can multiply diag D by A. And can people see what it's doing to the rows here? So what would the first row of diag D times A be? Exactly. So everyone get that? It's D1, which is a scalar value, remember, just the first element of this vector D, times A1 transpose. That is the first row. The second row would be D2 times A2 transpose. Okay, all the way down to DM times AM transpose. So what pre-multiplying a matrix by a diagonal matrix does, we multiply on the left by diagonal matrix, that is scaling the rows of that matrix. Now, alternatively, and actually I'll let people write this maybe for a second, but alternatively, we could write A by its columns, in terms of its columns. So I'll just do that quickly here, hopefully not mess people up too much. Write A by its columns. A1 is now the first column. They're not the same size as before, of course, remember, as we talked about. AN. And now let's talk about a vector D in Rn. Well, in this case, we can't pre-multiply by it. It's not this, right? Diag d is n by n, so we can't pre-multiply it. But as you may be guessing here, we can multiply on the right by diag of d. So a times diag d is, for the same exact reason, it's going to be d1 times the first column of A. That's the first column of this matrix. d2 times A2 is the second column, all the way up to dn an. Right? So multiplying by diagonal matrix on the right, and I should say, does that make sense to everyone, why this is the case? So let me just write it out here. So d is going to be, so A equals this. I'm going to write this diag d here. Let's see, I'll say this equals this thing. This thing. So this is going to have zeros here. So d1 is going to have all zeros. And the rest of the elements here, still zeros. And so let's look at what the first column of this thing is, right? So the first column of this product here is going to be this entire matrix times the first column of that. But when you multiply this whole matrix by this column, remember, multiplying a matrix by a column here, you can think of it as a linear combination of these columns given these coefficients here. But all of them are going to be 0 except for d1. So basically, this whole first element, the coefficients of these A terms here are 0 except for the first one, which is coefficient is d1. And so that's why it's scaling the columns of the matrix by d. Now, if you can't remember which is which, do you scale the rows, scale the columns? Just think about the size of these things. Okay? So if you're multiplying on this side, so remember this is m by n here. If you're multiplying on the right here, and you want a matrix that's the same size as A, you have to multiply by an n by n matrix, right? And so it has to be scaling the columns because there are n columns there, and that means the diagonal matrix will have n diagonal elements on it. If you multiply on the left, it has to be m by m, and then it has to be scaling the rows because there have to be m different elements in the rows. Another really nice use for diagonal matrices is doing things like getting element-wise squares of a vector. So I'm going to give you a vector here. Does everyone have this written down? OK. So let's give a vector x in Rn. And I want to now create some vector which has the elements of x that are squared. OK? How do I get this vector here? You want to take a guess? Yeah?
You must have a diag of that.
Right, exactly. So the problem here is you can't write something like x times x. Right? That doesn't make sense. This is n by 1. This is n by 1. It doesn't make sense as a vector matrix product. In MATLAB, of course, you can write x dot times x. But we're not talking about MATLAB land here. We're talking about the sort of the nice matrix notation land. You can write this x transpose x, but that's all these elements added together. That's the scalar value, right? Or you could write like x transpose, but that's an n by n matrix. None of these are n by 1 vectors. The way you do this is this thing is equal to diag of x times x. So first of all, this makes sense, right, in terms of multiplication, because this is n by n. This is n by 1. So this product will be n by 1. And remember, what you're doing here is you're scaling the rows, which in this case is just each individual element of this vector x, by the diagonal elements here. And what that's going to give you then is each element is going to be x squared. Now, here's another question. How would you write, sort of in completely valid matrix multiplication notation, we have a matrix A, m by n. How would you write, and we'll have C being a scalar. Remember, we said we could do this, right? We said I could write C times A as my one invalid matrix multiplication that I'm just going to take to be the element-wise product of, sorry, not the element-wise product, the scaling of each element of A times C. How might you write that more correctly in matrix notation? Any thoughts? So diag C, almost. Diag C is actually just C, because C is a scalar value. Right? So we need actually I think you have the right idea. What we want, right, is we want to multiply A by some matrix that has C's on all the diagonal elements. Multiply that by A. That would be scaling each row of A. We could do it on the other side too, but either way. That would be multiplying each row of A by C. That's sort of the right thing we want. But how do we actually get that with matrices? Yeah?
You said diag C times 1 times N?
Yeah, that's almost exactly right, except I would just correct you quickly and say diag 1 times C. Because 1 is n by 1, we assume it's always a vector. So this is actually a valid matrix multiplication here. It's a very nitpicky point, because actually you could write C times 1 just as well in using that sort of cheat that we have. But this is all valid matrix products now. So diag 1 times C times A, that equals C times A. It's cumbersome to write this, though, of course, and it's such a common operation that there's no need to write this all the time. So that's sort of a little aside there, but that would be how you write it kind of correctly. I kind of reached that kind of quickly there. Sorry if anyone missed that. All right, moving on. The inverse. We've seen the inverse already, but the inverse of a square matrix. Let's talk about a square matrix now. We will only worry about inverses for square matrices. Non-square matrices may have inverses. They have sort of other analogs of inverses. Sometimes they may have many inverses, depending on which side you're multiplying by, but we're not going to worry about that, left and right inverses, that kind of stuff. We're only going to talk about inverses of square matrices here. So we have a square matrix. Its inverse, which we denote A to the negative 1, is the matrix you multiply it by to equal the identity. So A times A inverse equals, A times A inverse equals the identity. Which also, by the way, equals A inverse times A. These are both n by n here, and here you can actually do the multiplication on either side. So multiplying with the left or the right by A inverse will both give you the identity. Now, the way, first of all, a couple comments. This may not exist, the inverse. There are all sorts of conditions that are required for it to exist. They're all equivalent, of course. One of the simpler ones is that A inverse exists if and only if A times a vector x cannot equal 0 unless x is the 0 matrix. Sorry, the 0 vector. So of course, if x is all zeros, then A times x equals 0. But for any other x, that can't be true. And what sort of this means is, so we have a matrix A here, right, written like this, right, A2, AN times x. This, remember, is some linear combination of the columns of A where the coefficients there are x. So if this can equal 0 for some x that is not equal to 0, what it means is that some linear combination of these columns essentially cancels out another linear combination of other ones. Right? So say maybe this column, A to A sub n, is actually some linear combination of these ones, and so therefore if you put a negative 1 coefficient on this term, that would actually equal 0. So we're not going to talk about this in any detail here, because we're not going to use these terms, but this brings up issues like linear independence. Are these vectors independent or not? Can some be combined to give you the other one? This is all related to the inverse. And so we actually will encounter some matrices that do not have inverses. We will see that. And when we see that, the way I'll show it does not have an inverse is I will give you a vector such that it equals 0. And that proves that A is not invertible then. I'll give you a non-zero vector for a matrix that A times that vector equals 0. That's how I will show it's not always invertible, or in fact, in that case, it's not invertible. As you probably saw from last time, a big use of the inverse is to do things like solve linear equations, right? So if you have a linear set of linear equations, ax equals b, well, the way we actually solve this, and again, I'm not talking about the way the computer solves it, I'm talking about the way we solve it, so if you just give an explicit expression for x, it's almost trivial here, but what you're really doing is you're multiplying A inverse on the left of both sides, so that you can do that. You can multiply both sides of the equation by A inverse. And then this term here is just the identity, by definition, of the inverse. So this just gives x equals A inverse b. That's really what's happening when we're solving an equation like that.
Professor?
Yeah?
Is this lecture also mostly a review of linear algebra?
So we're also going to jump to the matrix calculus and then MATLAB. So we're going to cover all of that today. All right, so a couple things now. Functions. So functions, you may have been more familiar with functions of, and this is sort of an notational thing that you might not have seen before, and it's very important for this class, because we're going to deal a lot with functions of matrices here, and functions of vectors. So you may be familiar with functions like f of x equals x squared. That takes as input a scalar value and produces another scalar value. But we're going to deal with functions that can really have arbitrary inputs and outputs. So for example, or arbitrary matrix valued inputs and outputs. So for example, a function could actually map m by n matrices to p by q matrices. Now we've seen some functions already, right? So for example, the function of A, if we define this as being the transpose of A, well, this is now really a function from m by n matrices to n by m matrices. Right? It's lots of other functions that could be the same form as that, but this is one particular function that is mapping m by n inputs to n by m outputs. The inverse is also a function. The inverse, I won't write these down, but the inverse is a function that takes n by n matrices as inputs and outputs another n by n matrix. It's another matrix function. So is multiplication, right? So multiplication, if we have a vector x in Rn, then the function defined by a times x, for a being an m by n, that is a function that takes as input n-dimensional vectors, right? Because you need to multiply an n-dimensional vector by this matrix A. And it outputs an m-dimensional vector. So these are all examples that we've already seen of matrix functions. And it's just important to think of these as being functions so that we can perform certain operations on them. So let me talk about now a few specific categories of functions. And I'll go through this pretty quickly, because there are some things you will see, but the details here might not be that important to know. So one very common type of function is what's called a vector norm. So this is a function of a vector that outputs a scalar value. So norms are functions they are functions f from Rn to R. Take vectors as inputs, output a scalar value, with certain properties, though. I'm just going to list these. You don't have to worry about them too much. More important sort of to know some of the examples of them. That's how you'll become more familiar with norms, I think. But first of all, norms always have to give it a number greater than 0. Norm is, in a sense, a measure of the size of a vector. And so we don't want the size to ever be negative. That's not. We're going for sort of, or a measure of the magnitude, I guess, of a vector, where magnitude typically is defined one way, but can be defined in a lot of ways by these norms. The other thing is, second property is called, and also the norm is 0 if and only if x is 0. So it can't be 0 for anything but x being equal to 0. The second property is called homogeneity. It means that if you multiply the vector a by a scalar, take the norm of that, that will equal the absolute value of a times the norm of x. And so in some sense you can think of a being, or the norm being kind of like a generalization of the absolute value two vector inputs. Of course, there are many different possible generalizations of absolute value, but that's kind of what it's like. In one dimensions, this, of course, would be the norm would be the absolute value, for example. And this would clearly hold there. But in general, this property has to hold. So they kind of have to have this analogous property to the absolute value in higher dimensions. And finally, the norms have to obey something called a triangle inequality, which is saying that the norm of x plus y for two vectors x and y is less than the norm of x plus the norm of y. And what this means sort of graphically is that if you write these vectors, for example, in two-dimensional, it's pretty easy to write a vector as an arrow. And so if you have a vector x here and a vector y here, then this vector here is x plus y. And what this is saying is that the length of this by, again, some definition of length, the obvious one just being that we're used to is Euclidean norm, which is actually the L2 norm, which is one of the things we'll use a lot in this class. But the length of this, by some definition of length, is less than the length of that plus the length of that. Some common ones that we've already seen are the L2 norm. This is also just called Euclidean distance sometimes, or Euclidean norm. Actually, no, sorry, distance means like it would be x minus y, the 2 norm of that. But this is called the Euclidean norm sometimes. Another one, though, which we may not have seen before, is the L1 norm. And that is also something that satisfies all these properties. This is sort of the natural thing, right? Because we sort of know that this satisfies things like that. We can picture it geometrically, all that kind of stuff. The L1 norm is a different thing here. It's the sum of the absolute values of the elements of x. And that actually satisfies all these properties as well. So now let's talk about, again, as I said, one of the sort of the more interesting things that isn't always taught in linear algebra courses, but it's going to be really important for this class. And the examples here are actually pretty simple. We actually already covered this one here. But very often, what you're going to find is you're going to form some vector or matrix expression where you're writing these things out term by term. Right? So you have some vector or some function where you either have a sum in it, or maybe you've written out, a big matrix where the only way you can describe it is to say, okay, this is going to be x1 minus y1, this is going to be x2 minus y1, etc. Things like this. You're going to define matrices or functions in terms of sums of elements, or in terms of their sort of explicit elements one by one. And it's very useful to be able to have some intuition about how you take these seemingly complex expressions and convert them into a vector form or a matrix form that's typically is saying the exact same thing. So we're not really simplifying it at all here. I don't want to use that term. We're just kind of writing it a little bit more compactly. And that can oftentimes make it much easier to actually see what's going on. OK, so we actually already did this one, but I'm using different symbols here, so hopefully you can all figure out how to extend it from last time. But what if I have this function? So I have a matrix, or actually rather, let me see. I have a bunch of AIs. Each of them is an Rn. I have a bunch of BIs. Each of them is a real valued number. I have m of these, each of them. And I have my function x, this is a function that takes as inputs vectors in Rn and outputs a real valued number. And my function is going to be defined as the sum from I equals 1 to m of AI transpose x minus b squared. So how do I convert that to vector form, matrix form? Who just want to yell out what it is? You'll have to define some matrices to do this, by the way. You'll have to say A or big B or something equals something. But does anyone want to take a guess about how you do that? So maybe start by writing a matrix A. Well, I'm trying to do this in a way that doesn't give away too much here. suppose I had a vector y, where yi equaled ai transpose x minus bi. What would this thing be then? How would I write that? Fx equals what? Remember, it's the sum of all these elements squared, so what would that equal in terms of y? It's the sum of them.
Yeah, it's y transpose.
Yes, exactly. Right, does everyone get that? So this would be equal to y transpose y, with y defined like this. Remember, y transpose y is the inner product of y with itself. It's the sum of all the elements of y squared. X is our input to the function. X is a vector. It's going to be a vector in Rn. I erased the actual function definition, but I'll just write this like here. X is a vector in Rn. Yeah, it's the input to the function, exactly. We're thinking about vector functions that take vectors as inputs. So, okay, so this would be y transpose y, which we can also write. Can we also write that a different way, actually, from the previous slide? Not diag, just the actual previous slide right before. Yeah, so it's just going to be the L2 norm of y. What though? L2 norm by itself? Right. Okay, you can do it either way. I mean, if y is a really long expression, you might save characters by doing it this way. Otherwise, you might save characters by doing it this way. Okay, so now, how do we define a vector y that looks like this? And you can do that, by the way, by defining any sort of matrix A in terms, or matrix A or vector B in terms of these sort of individual elements here. Might be a little confusing because I'm using the same. Maybe let's you don't have to even use the same characters here. Let's find a matrix C and a vector D. Can you describe a vector Y that has this property here? So what this is doing is this is saying really y, let me write it out maybe more, y equals this big vector. It's going to be a1 transpose times x minus b1, then a2 transpose x minus b2, all the way down to am transpose x minus bm. So is there any guess about how you would define some matrices to define this a little bit more compactly? So this part here, right? So you're subtracting this thing here. I think you're making it too complex. Yeah, it's pretty straight. It's just a few characters here, really. Any guesses? Yeah.
I guess ax minus b, where b is a vector of all the bi's.
Where b here is a vector, right, of all the bi's. b1 to bm. And what's a?
And a is a matrix with all the ai's as its column.
Close. What's the other possibility?
Yeah, transpose the rows.
Yes. Okay, does that make sense why that one was the right answer? So A here is a matrix with A1 as the first row, all up to AM as the last row. So this Y equals A x minus b with these definitions. Does anyone that I guess there's two elements here, right? One is after the fact, being able to figure out that this thing equals that. And the other one is going from this to say, let's construct a matrix that makes this equal to it, and going from this to this, which is a little trickier. But hopefully you'll get familiar enough with these that you can do this. Does this way make sense to everyone? Going from this to that? OK, so this one's a little bit harder, but if you can do the reverse, you can do it the other way too. You have to just think about, instead of all possible things that it could be, and then pick the one that's right. So finishing up then, what is one way of writing? I'll erase this now. How do we write f of x compactly? Times what? Yeah. So we can do it like this. Remember, these are vectors themselves. This is a vector in Rm. So this is just an inner product of two vectors. Or you could write it just, again, as the L2 norm. We've already seen the example here with using diags to make a vector of everything squared. OK, so this is probably actually the trickiest linear algebra that will occur in this course because it's not ever taught. We never teach people how to sort of construct things in vector form. We just always give them the vector forms or the matrix forms. But you will have to do a little bit of this. So this is sort of you'll get some practice with this. So one last thing I want to mention in terms of linear algebra, because you've probably studied it if you took a linear algebra course, is eigenvalues and eigenvectors. Who here has studied eigenvalues and eigenvectors by a show of hands? OK, so most people, but not everyone. So we're not going to really use these too much in this course. But they will come up a little bit in the very last unit. And really, they're only going to come up in this context here, this one example here. So if you understand this one example, then you'll be able to understand everything. The weird thing with eigenvalues and eigenvectors is people are often taught them, and they're taught them by that equation. So what they're told is that we have a matrix A. We're only going to talk about eigenvectors and eigenvalues of square matrices here. So this is an n by n matrix. Eigenvalues do not exist for a non-square matrix. There's other generalizations that do exist, but we're going to talk about square matrices here. An n by n matrix, we say that x is an eigenvector and lambda is an eigenvalue if they satisfy this equation. If a times x equals lambda times x. What this means is that a, multiplying by a, doesn't change the direction of the vector in some sense. It just changes its magnitude. OK? So basically, this is a scalar value, and this is a matrix product. So what we're saying is that this matrix product does not change the direction. Basically, if we have x being like this, multiplying by a doesn't change its direction. It just sort of stretches it out or maybe makes it a little shorter. Now that's sort of an intuitive notion, but a couple things are weird. First of all, even when a has real values, it's actually the case that both the eigenvectors and the eigenvalues can be complex valued. So this is a complex valued vector of n dimensions, and lambda is a complex valued scalar. Now, we're not going to really need that property, so don't worry about why that is. It boils down to the solution of polynomial equations, but don't worry about that. But again, after this fact, a lot of people don't really talk about eigenvectors and eigenvalues beyond this, and so it's really unclear why these are actually useful. So I'm going to give one example about why they're quite useful, or an analysis that you can do with eigenvectors and eigenvalues that is quite useful. And this will actually come up later in the class when we talk about control. So let's first, actually I'll just define it like this. But what I'll do is I'm going to take, now and I won't prove this, but for an n by n matrix, there are at most n different eigenvalues and n different eigenvectors. It's actually possible that sometimes these can be repeated. You could have the same eigenvector or the same eigenvalue. That can cause nasty situations. It's also the case that if, well, actually, there's two things here. So first of all, if x is an eigenvector, then any constant times x will also be an eigenvector, right? So we're going to actually always assume that eigenvectors are have norm 1, so that we sort of normalize them to have unit norm. So that's sort of not the different way they can be all the same. But it turns out that in some cases, there aren't n independent eigenvectors. There are only maybe n-1 or n-2 of them. Those are not good matrices. We don't like those matrices. And we won't deal with those in this class, so don't worry about it. But let's assume now that there are n independent eigenvectors and n eigenvalues. We can take that equation and write it down n different times. So we take sort of all of them. We form a big matrix. It's where these are the columns of the matrix. This equals, then, if we sort of do things correctly in terms of diagonal matrices here, this equals this same vector here, where each term is scaled by the corresponding lambda, x2 lambda 2, right, which is just equal to this same big matrix X times the diagonal matrix of all the lambda values, so lambda 1 to lambda n. OK? So I'm just using that trick of scaling the rows as multiplying by a diagonal matrix. Let me call this matrix X. Sorry, it's because matrix X, and I'm going to call this matrix lambda. Now, what this equation says is that A times X equals X times lambda. Or if we assume these are all independent eigenvectors, all I mean by that is that we can invert this matrix. So A is equal to lambda X inverse. OK, so I went through a lot of steps there. And again, don't worry about the steps here, because it's really not the important point. The important point is that you can write a matrix that's that has certain properties. You can't always do this, but the ones we'll deal with, you always can. You can write a matrix as x lambda x inverse, where lambda is a diagonal matrix. OK, that's the important point here. And those diagonal elements end up being the eigenvalues of A. So now, I'm just going to erase this here and write this one expression, because this is all that we actually care about. I just kind of went in a roundabout way of getting it. So now we have A equals x lambda x inverse. Remember, A is square here, so I can multiply A by itself. So what does A squared equal? Does anyone want to guess that? Or just write it down? Yeah, so let's just write it, actually. X times lambda x inverse, x lambda x inverse. And of course, what you see here is that you have x times x inverse here. Those cancel out. I won't erase that. Those will cancel out. So what you get is x lambda squared x inverse. Now, for a diagonal matrix, squaring it is very easy. Right? You just take the individual elements and square them, because as if you were scaling each row or each column by each element there. So you're just, lambda squared is going to be equal to, well, lambda 1 squared all the way down to lambda n squared. OK? So this is actually kind of cool, because matrix multiplication is kind of expensive, right? You have to sort of compute every single element there by, a sum from each element is a sum over the rows and columns all added up to, multiplied by each other and added up together. Whereas here what we're doing is we're first decomposing it into its eigenvalues, and then we're just squaring one number. And we can get any power of A very quickly by just squaring lambda as appropriate. And by the way, MATLAB will let you do this pretty easily. It's not hard to do that in MATLAB. Squaring each individual element and just computing this thing instead of computing the product here explicitly. What's even maybe more interesting is that now we can analyze behavior like what happens to a to the k as k goes to infinity. And we'll see why this actually becomes really relevant later on in this class. But this is sort of a question that seems kind of hard to answer, right? We're talking about matrix multiplications again and again. That seems tricky to answer. But the nice thing is that with this little formula, we actually have a pretty easy way of doing that. So we can just think about scalars with this property. So for a scalar value, for lambda, what happens to lambda to the k as k goes to infinity? Or rather, if lambda was, say, 2, what would happen to this? I mean, just would it get bigger or would it get smaller if lambda was 2? Right. So lambda squared is 4, lambda to the third is 8. It would get bigger, and this would go up. This would go to infinity as k goes to infinity. But what if lambda is equal to 1/2? Right? In that case, this goes to 0 as k goes to infinity. So this is really interesting, because what this says is a matrix as a whole, every element of that matrix, in fact, that's proving that formula is a little bit tricky, but it ends up being actually every single element of that matrix. If you keep multiplying it by itself, that whole product will, every term there will go to infinity as long as there is one eigenvalue greater than 1. If, on the other hand, all the eigenvalues, as long as 1's greater than 1, then one term here could get big and the whole thing is big, potentially. I guess you could potentially have only some rows and some columns getting big, but in general it's going to be sort of every row here gets big. Or every element gets big. But suppose that every eigenvalue was less than 1. Right? That means this term here, which was lambda a to the k, would be lambda to the k times this. Every element here would go to 0. So this thing would go to 0. And you multiply any matrix by 0, it's still 0. So a to the k will, in fact, go to 0 as k goes to infinity. This is very interesting. This is called a stable matrix. Don't worry too much about this. Again, these are all sort of things that will come up a little bit in class, but this is actually a topic that's more advanced than what we're going to actually cover in class. This is the only sort of use we have for eigenvalues here. So we do have this property, but it's sort of one of the most interesting uses of eigenvalues, because you've probably seen them before, but maybe they didn't seem that useful. They're actually incredibly useful, and you can prove all sorts of things like this sort of stuff, right? Like if I keep multi-matrix by itself, what will happen? That's really hard to answer without recourse to eigenvalues, but it's really easy to answer in that case. So that is the end of our linear algebra review. That's all you're going to know about linear algebra. And again, I think probably most of that is review, at least the definitions will review, though maybe some of the tricks we play, like how you convert things to matrix form, that is probably not review, because again, it's not really taught anywhere. And this might not be reviewed. This is fine. This is not reviewed, by the way. This will not really need in class other than this one property we're going to use, which I've already kind of proven. OK, so now let's talk and get the second topic. And we're not going to have time to finish the MATLAB review, but we'll hopefully at least start it. OK, so there are three. So now in this class, we're going to use some calculus. But the good news is it's really simple calculus. Remember calculus, you took calculus and they did derivatives first, then integrals. And you spend all your time doing integrals because integrals are half of them don't exist. Half of them you have to do all sorts of crazy manipulations to get them in a form that you can write. We're not going to do any integrals in this course. So that's the good news, right? No integrals. Just derivatives. In fact, just derivatives of like polynomials, which are really easy, right? There's a simple rule for that. You can write a program that does that. Really, really simple calculus. The only hard part is that we're going to do it for matrix functions. So remember, typically you have calculus where your functions are, taking as input real value numbers and output real value numbers. You can take the derivative, second derivative. You can integrate those things too, though we're not going to do that. Because you'll see in a second, it would be really, really hard to integrate in a lot of cases. So we have all these things. But we want to now define analogs of derivatives, and maybe second derivatives, for vector-valued functions. And matrix value, actually no, sorry. Vector-valued functions, and actually we'll just worry about functions that take vectors as inputs. We won't worry about things that take matrices as inputs. But vector input functions, and either real-valued functions, real-valued output functions, or vector-valued output functions. Okay? So the only reason why this is hard is that it just looks a little bit more cumbersome than you might be used to. The rules themselves, if you break it down to the actual element by element math, is incredibly simple. In fact, we did some of these last time with the gradient. That's one of the cases we'll deal with. But it's just good to know. Here we're going to sort of present all the different forms that we'll use. There's only 3 of them. They have funny names, but you just get used to it, and it'll be fine. So there's 3 things that we will use here. And I'll just write them side by side, actually, even though I have them here all on different slides. So there is the Jacobian. And you may have heard, actually, has anyone taken here multivariate calculus and heard these terms before? So who's heard of Jacobian before? OK, oh, actually, excellent. Everyone has. So there's a Jacobian. Who's heard of the gradient? I guess we talked about it last time, so everyone better say yes. Who heard of it before? OK. Oh, even better. And then the Hessian. Who's heard of the Hessian? OK. So maybe some people haven't heard of that one, but it's equally simple. So I'll go through this fast. There's the Jacobian, there's the gradient, and there's the Hessian. These 2 are both analogs of the first derivative. This is the analog of the second derivative. The Jacobian, the only difference between these 2 is that Jacobian is defined for functions that take n-dimensional inputs and produce vectors. Take as input a vector and produce a vector. That's something like a times x, right? That could be a function that would take an n-dimensional input and outproduce a vector of dimension n. The gradient we're only going to talk about, it's a special case almost of the Jacobian. Special case of the Jacobian, and then you transpose it for odd reasons, but you transpose it. The gradient, we're only going to talk about functions that are vector-valued inputs and real-valued outputs. And remember, part of the reason for this is, if you remember from last time, we talked about minimizing a function, for example, using its gradient, setting the gradient equal to 0. Now, you can only minimize, it only makes sense to talk about minimizing a function if it has a single output. If it has multiple outputs, you can't, what does that even mean? There's 2 outputs. You can't minimize both of them at the same time. Maybe you can, but you probably can't. So the gradient we're going to use only in situations where there is a real value output. And similarly, the Hessian we're going to talk about only in cases where there's a vector valued input and a real valued output. And this one's going to be the analog of the second derivative. So let's just define each of these now. So what the Jacobian is, the Jacobian is a matrix, and we're going to call it dx f of x. That's how we're going to denote it. It is a matrix which is m by n, where each element is defined as the following. dx f of x. The ij element of that thing is, and if you're like me, I still get this wrong sometimes, the order, when I'm writing it quickly, so don't feel bad if you forget this order here, is the derivative of the ith element of f. Remember, f here is produces m-dimensional outputs. So fi of x, we'll call that's the ith element of that output vector. The partial derivative of that with respect to xj. And by the way I remember this is I remember it in terms of the gradient, and I just remember, but we'll get to that in a second. So what that means is this is actually an m by n matrix, right? Because there are m outputs to f, and so there's the number of rows in f will go from 1 to m. And I'm just writing it out here a little bit more term by term. The first element is the derivative of f, the first output of f with respect to x1. Then the rows take derivatives with respect to that same output, but then with respect, sorry, the derivative of that same output with respect to x1 to xn. And the first column here will be all with respect to x1, the derivative, but the derivative of the different elements of f. So for example, if x is a scalar and it outputs a m-dimensional vector, then then the Jacobian will be the same size as that output, and it will just be each of the derivatives of the derivative with respect to the input x of each of the different outputs. So let's take a simple example here. I'm defining this f of x equal to this thing. Actually, I won't write that. It's here. Here's the equation. What's the Jacobian here? This is a function that takes three-dimensional vectors as inputs, outputs outputs a two-dimensional vector. So first of all, how big is the Jacobian for this guy here? Right. So d f of x, that is a 2. So there's 1, 2 by 3 dimensional matrix. What's the first element? Not quite. Right. So this is a constant with respect to x1. So it's a constant times s squared. So it's going to be 2 x1 times x2. What about the second, about the 1, 2 element here? People are shouting out the right thing, but yeah. It'll be x1 squared. And what's the third element? It's going to be 1, right? Because take this derivative here. Ends up being just a constant 1. What is the 2, 1 element? It's 0, right? There's no x1 in this last thing here. So it's a constant for that purpose. Fine. What's this next element? Right, 1 over x3. And what's the last element? Wait, there's something. No, not minus, not x2.
Minus x2 over x3 squared.
Yes, everyone see what that is? OK. Everyone remembers there, right there. Derivatives. This is the one that was a little, I threw it in as a little, see if you did remember your derivatives, right? But you know, it's very simple if you do it element by element. This is just sort of the simplest calculus you can imagine. So it's not hard except the fact that you write these out by bigger numbers here. Actually, typically write these out kind of in brief notation. By the way, we typically in this class are not going to be writing out derivatives like this, where we just take every element. You can do that, but then you want to go back and put it in matrix form after all that, right? Because it isn't that useful to have a lot of times sort of every element by every element. So let's take a simple example. F here is an Rn to Rm, just defined as f of x equals ax. Okay, A is an m by n matrix. What is the Jacobian? Yeah.
Just A?
It is just A. Okay? So remember, this is a vector here where, for example, the first row equals A1 transpose. That's the first row of A times x. That'd be how you find the first element. So let's think about what that means sort of in terms of Jacobian then. What that means is that the first, basically the derivative with respect to this first element is going to be the individual derivatives of this inner product here. And that's going to be the first column of this, the first row of this matrix, Jacobian. Right? Because the first row of the Jacobian is going to have, partial this term, A1 transpose x, with respect to x1. then partial A1 transpose x with respect to x2. That'll be the first row of this thing, right? Well, what is this? This first term here. Well, no, just this first one. So this is a scalar. This is a scalar here. What is that? I guess it's hard. It's the first element of this vector, right? It's it's A1, A1, 1, and this is sort of A1, 2. But really, this is just A1, 1. This is A1, 2 in matrix form, right? So you have a big vector here that just, if you go through it, and by the way, you should do this if you aren't convinced yet. If you go through this, what you'll find is that each element ends up being just the exact corresponding element of A. This is A11, A12, A13. This is A21. And so you just actually get A there. OK. So that's the sort of thing you may not have seen before that we're going to do still. But that sort of goes into that same category, right? Everyone could do this. So that goes in that same category of you taking a big matrix expression where you maybe write it out term by term and converting it to an actual just simple form. Here it was very simple. And it was intentionally simple. That's sort of why the Jacobian is that way, by the way. That's sort of the prototypical example of a first derivative there. OK, so the gradient is the next thing we'll think about. The gradient is also a first derivative. It's just a special case that only happens when x is vector input but scalar output. And in fact, in this case, the Jacobian, right, would be so the Jacobian here of f of x would be a row vector, right? Because you would take, there's one output, so you only have m here is 1, so you have a 1 by n matrix being the Jacobian. And all I'm going to do is say, let's take that and let's transpose it. We're going to call that the gradient. You can also write it out in this way, but it's also just thought of as the transpose of the Jacobian. So the only reason why we do that, by the way, is that it's sometimes a little bit easier to work with column vectors than row vectors. So we just have its own name for it. And we'll denote it like this. It's upside down arrow x, f of x. That's the gradient. It's just the vector of partial derivatives. x1, partial f of x, xn, which is also equals the Jacobian of this thing, the x f of x transpose. OK. And remember last time we did some sort of common rules of the gradient. Oftentimes, like when we're minimizing a functions, for example, as I keep pointing out, we'll want to use the gradient. It's a little more natural than Jacobian, just because it's by nature a vector. We don't have to transpose it to become a row vector, a column vector. And finally, there's the Hessian, which is just the analog of the second derivative. So when you have now a vector valued function, sorry, not a vector valued function. Function takes vectors as inputs, outputs a scalar value. And I should say, I'll just keep writing here. Let's upside down. So the gradient, or in this case, x is a vector in Rn. The Jacobian, which we'll just denote like this, now upside down arrow squared, triangle squared f of x. That's going to be an n by n matrix. And it's going to be an n by n matrix of all sort of possible second derivatives here. Because when you take the first derivative, you have actually a vector of all possible first derivatives. Then you take each of those terms and take the derivative again with respect to all possible x's. So a very simple way of actually writing this is that the Hessian of f of x, remember, you can think of the Jacobian kind of as itself a function, right? Because it takes as input actually, I won't say that. You can think of this when you plug in a value of x here as taking a value of x, which is in Rn, and outputting a vector in Rn. So in some sense, that is itself a function of x. And the Hessian is just the Jacobian of that function. We just sort of take the derivative again. But you have to call it Jacobian now because this is now a vector, and we're taking, so it's a vector valued input, vector valued output. So it's just the Jacobian of the Hessian, sorry, of the gradient. But maybe a little bit more concretely, what it is really is it's the square matrix where you have partial derivatives here with respect to, say, in the first time you have derivative x1, x1. I can write that as x1 squared, but I'll just write it like that. The next time you have squared f of x, partial x1, partial x2, down to f of x, partial x1, partial xn, and etc. This will be then with respect to xn squared. And this, interestingly, will actually be a symmetric matrix, we know, right? Because this term here, for example, is the partial with respect to partial squared with respect to f of x of derivative x2 partial x1. And it does not matter in derivatives, remember, whether you take one derivative first and then the next derivative, or one derivative, derivative with the x2 first, then with respect to x1, or x1 first and then with respect to x2. This is going to be the same thing as that. And so by the nature of this construction, the Hessian is going to be symmetric. So that's sort of an example of things like symmetric Hessians coming up. Take one example. I'm not going to get too much MATLAB, but I'll at least introduce it a little bit maybe, and then we'll get to the nuts and bolts next time. Take a simple example, which is f of x equals x transpose A times x. Okay, let's check to make sure that this makes sense, first of all. This function, x here, is a vector in Rn. A is a matrix, which in this case is n by n. So what is this Hessian? And in fact, I'll even let you use a rule from the last slide and say that the gradient, I'll just write it again here, the gradient with respect to x of f of x here is equal to A plus A transpose times x. That's sort of the analog, the matrix analog of the case that, if you have something like ax squared, then the first derivative would be equal to 2ax. This is the matrix version of that. So what's the Hessian then? This is the gradient. Any ideas? Yeah. You're right. So it's just equal to A plus A transpose, right? Because this term is the gradient. Remember, the Hessian is the Jacobian of the gradient. I'm using a lot of terms there, all 3 in 1. But remember, we proved before that the Jacobian of A times x, just A. And so it's just this. It's just this thing in here. And as you can see right now, this is, of course, symmetric, right? I mean, I didn't really prove that because the only reason we sort of got that was because I gave you this rule here. But you can derive this rule element by element and figure that's right. This is actually a somewhat tricky one, so it's good to do and see if you can do that. So let's see. OK, we have 10 minutes left in class to start doing a MATLAB review. I want to just do it maybe very briefly, but I'll get to probably going through the actual stuff next time. But I just want to maybe introduce everyone to MATLAB because we're going to use it a lot. And so for those that haven't ever fired it up before, it should be useful. I actually was going to check to make sure the resolution and everything was right, because since I changed the contrast on the video, we may no longer get very good picture when we actually have a non-slide up there, or I'm not writing on the board. But I won't do that right now, because that would take probably the rest of the time we actually had. What I will do instead is just fire up MATLAB and see if it actually works. I wonder if you can actually see me. I'll be really sort of cut off down here if you can see me at all in the picture there. But I'll maybe adjust that for next time too. So OK, first of all, let's quit that. And let's open up MATLAB. So MATLAB is, in terms of it's sort of an interesting environment, because it's a programming language, but it's really more kind of just a way of interacting with data and plotting data and storing data as matrices and vectors. And it can be really sort of nice for doing that. So let me first go ahead and make, boy, that's really small, huh? Let's see if I can make this bigger. Huh. OK, let's make this like. That's still kind of too small. So it looks like I'm going to spend the entire time getting this set up to look right on this projector, because my projector was different from before. OK. I also didn't realize how hard this would be, because I can't actually see my screen, the screen here. Let's make this 20. OK, there we go. So MATLAB is basically a language for interacting with vectors and matrices. You can have all the basic operations, like 1 + 1, that gives you 2. By the way, if you don't want, you oftentimes will not want to have the output there. So if you say 1 + 1 or say anything and put a semicolon after the line, that will suppress the output. You can do things like divide numbers too, or raise them to the power of something. You know, that's all pretty standard. You'd hope to do that in basically any language. I guess actually you can't in C, right? You can't raise things to the power in C, but you can do it in a lot of languages. But what MATLAB's very good at, and I'll just say this for now, and then we can get to the actual details next time, is MATLAB is very good at handling easily matrices and vectors. Right, so it's very sort of natural doing matrix and vector manipulation. You can do multiplication just as like you're multiplying two numbers. And so it's very nice for that reason. So for example, well, first of all, we can do things like makes, A equals 1. So A equals 1. We can do things like scalars, where we're setting the value of A now. A is now a variable that has the value 1. In this case, A is a scalar value. We can also, there's some things built in, like pi is built in here. So we can set B to be equal to pi. And we can, of course, add A and B and stuff like that. But what's nice, really, is that we can easily specify things that are vectors matrices. So let's maybe define a matrix now, where the first two, 1, 2, 3, 4, 5, 6. Oops, 5, 6. OK. So that gives us a matrix now, which is, in this case, 3 by 2, where the elements are what I typed in. So these guys here, semicolons mean you're just starting a new line of the matrix. We're going to enter matrices by rows in this. So this is the first row, second row, third row. If you actually didn't need that last semicolon there. If you enter a matrix that's the wrong size, like if you try to do this, A equals 1, 2, 3, MATLAB will complain and tell you that's not OK to do. You know what? Actually, we do have time, so I'll just do a little bit more. First of all, actually, maybe ask, who here has used MATLAB before? OK, so everyone has. So then you all know this. So this is simple stuff. So maybe I'll just start going through it quickly, because I think people that aren't here also left because they already know MATLAB. OK, you have things like A transpose. That transposes A. Actually, the prime there is actually the conjugate transpose. So if A is complex valued, it will transpose A and also negate the complex portion. If you want just the transpose, it's actually dot tick. That will only be important when we actually deal with complex matrices. But A tick is not transpose. A tick is complex conjugate. OK, you can make B a matrix too. So let's make B a matrix of the same size as A. And live demos are always sort of a risky thing, because I can't check my spelling, especially when I can't see when I'm typing. Do this, so then we can do things like A plus B. A and B are the same size, right? So we can add A and B, we can subtract A and B. We cannot multiply A and B, because A and B are not right dimensions to multiply together. We could do this little guy, right? A dot times B. That's the product. That's the element-wise product of those two things. But that's not multiplication, and we don't have good notation. I mean, you could write that in other notation for matrices, but we're not going to use that notation. We can do, of course, is multiply things like A times B transpose, because these are both. They both have A has 2 rows, and B transpose now has 2 columns. Sorry, A has 2 columns, B transpose has 2 rows, so we can do that. We can also do things like raise A to the 2nd power, and then, like multiplication, dot squared means we're taking every element of A and squaring it. So that's element-wise squaring. If we were to type this, that is not valid, because that's trying to multiply A by A. That's the same as this thing, and we can't do that, right? That's going to yell at us. What we could do is we have a square matrix, like, say, A transpose times A. That's going to be a square matrix. So that we can square. And this is different, though, from the element-wise square. This first one here is if you take the matrix, actually multiply it by itself. This is if you square the individual elements. So, of course, those are going to be different things. We can also create vectors. So x as a vector, say. If we just write like this, 2, 3, 4, well, that will be a row vector, right? Because we're essentially making a matrix with 1 row. We can write a column vector in other ways. We could just, for example, put semicolons there, and that would be now a column vector. Or we could do something, oh, by the way, up and down sort of gets you a history, so you can do that quickly. Or we could like transpose that row vector that we create. So those are both ways of doing it. Or if we want to be even sort of more MATLAB-y, we could write x equals 1 to the 4, and that will actually create a vector that goes from elements 1 to 4, progressing by default by 1 at a time. If we were to write something like this, we would get a longer vector where this is progressing things by 0.1 at a time. That's a big vector now. Maybe I'll make it a little shorter so you can actually read it on one screen, but that's the sort of shorthand for series and sequences like this. OK, I'll talk about special matrices, a couple of them now, and then that'll be the last thing. So we have a couple special matrices. There's things like 1s. So this will generate a matrix of all 1s, which is 2 rows and 3 columns. 0s will do the same thing, but they'll all be 0. Rand will do the same thing, except each element is uniform random between 0 and 1. So they're sampled uniformly between 0 and 1 randomly. And rand n will do a similar thing, except now these are all random normal numbers. So we'll use both of those actually a fair amount in class. Some more special ones. I is the identity of size n. So I of 4 is a 4-dimensional identity matrix. You don't have to write 4, comma 4, because identities are always square. And do we still have our vector x? Well, let's make x equal. Well, let's make it equal 1 to the 4. But let's transpose this with the column vector. We can also do things like use our little diag function. So diag of x is just a diagonal matrix with the elements of x in it. If there's one more thing we can do here, so let's maybe make a random 3x3 matrix. Diag actually has 2 meanings in MATLAB. It can mean either take a vector and make it diagonal, a diagonal matrix, or it can mean take the diagonal elements of a matrix and make those into a vector. So here the diagonal elements here are 9.5 something, or sorry, 0.95 something, 0.42, and 0.65. So if we write diag A, that actually also gives us a vector which is diagonal. So by the way, diag of x, that actually just gives you x, right? This one here is not valid in our matrix notation. It's only valid in MATLAB. There are going to be a lot of things that are hard to write in sort of valid linear algebra, but easy to write in MATLAB. OK, and lastly, I guess you can see what's actually, you know what? Let me end there. We're at time, so we'll finish up this. It probably won't take long because everyone here, even in the review session, already knows MATLAB. So we'll probably take 10 minutes or so to finish this up, or 15 minutes maybe, and then we'll get to sort of the meat of the stuff, which is optimization and other takes on that least squares problem that we talked about 2 lectures ago. So we'll see you next week.